In this class, we are transitioning to the application of the suspended growth reactors using the theories we have learned from previous classes. We have learned the modeling of suspended growth reactors with the most basic example of one aerobic biomass separator CSTR treating one organic substrate with one biomass group. We first write out the mass balance of various components in the reactor and use stoichiometry and kinetics to describe the reaction terms. From the mass balance, we have found the expression for various performance parameters such as effluent substrate concentration, active biomass concentration, debris concentration, MLSS, wastage rate, oxygen demand, etc. Then we extend the model to more complicated effluent that contains biodegradable and inert particles and active biomass. In real life, instead of an ideal biomass separator which represents an ultrafiltration membrane, the conventional configuration with a clarifier to settle down the solids after the reactor is more commonly used, especially in water resource recovery facilities. We can use the same principles to model the conventional configuration, but with three assumptions. After settling, the concentration of recycled MLSS equals to that of the wasted MLSS. The MLSS settles uniformly, meaning that the active fraction of MLSS does not change. Finally, the clarifier is a perfect clarifier, which means all solids enters the clarifier quickly settles, leaving no solid in the supernatant. Therefore, no bioreaction occurs in the clarifier. Then we can write the mass balance for MLSS for the overall system. This is the boundary for entire system that we are investigating. Because there is no biomass in the clarifier supernatant, so the mass of biomass in the effluent minus the mass of biomass wasted plus reaction equals to 0 at steady state. This is essentially the same as the biomass separator. We can then look at the mass balance in the clarifier. Now the system boundary becomes this. Because there is recycling, the clarifier influent flow rate is F plus FR. The supernatant is still 0 as all MLSS is settled in the clarifier. From the mass balance, we can use the influent flow rate, wastage flow rate, and recycle flow rate to express the ratio of MLSS in bulk solution and MLSS in waste streams. Therefore, we can express SRT with this equation. Although I have said that the conventional CSTR are most commonly used, in real life, the reactors are designed to be parallel long rectangular reactors that are not completely mixed along their axis, but perform more like PFR, in which the substrate degrade along the reactor. We can model this as CSTR in series, or using the differential volume method that I have introduced in topic 8. But the mass expression and solution can be very complicated. To simplify, we assume that the variation of biomass in the reactor is minimum. This assumption is valid when SRT is over 5 times higher than HRT. We can conduct a steady-state mass balance of the active biomass in the whole system of PFR, followed by a clarifier. We assume that the active biomass concentration XBHT average is uniform in the reactor. There's no influent biomass. The extra active biomass grown in the system is wasted. Please note that mu average represents the average specific growth rate, as the specific growth rate is a function of substrate concentration, which changes along the reactor. After rearranging, the expression becomes familiar. 1 over SRT equals to the average specific growth rate minus the specific decay rate. let's do a steady-state mass balance of substrate in a differential volume. The mass of substrate in minus the mass of substrate out minus the degradation equals to 0. After simplification, we can substitute the Monod equation in this expression. We can then integrate both sides of the equation from the entrance of the reactor to the exit of the reactor. This is equation 1 from the substrate mass balance. S is not the influence substrate concentration before being combined with recycle flow. SSI, the influence substrate concentration after combined with the recycle flow. And SSE, the reactor influence substrate concentration, are all used in equation 1. To find their relationship, we need to focus on the entrance of the system. At the entrance, the influent flow combines with the recycle flow before entering the reactor. So, the flow rate becomes F plus alpha F, and the substrate concentration changes from SS0 to SSI. We can conduct a mass balance at point 1, the combining point. SSI can be expressed with SSO, SSE, and recycle rate alpha with equation 2. Knowing equation 1 and equation 2. Next, let's conduct the steady-state mass balance of substrate for the entire system. At this point, can you pause this video and try to work on this yourselves? So, the mass of substrate gets in the system through the influent per time, minus the mass of substrate gets out of the system through the clarifier supernatant per time, minus the mass of substrate wasted per time, minus the degradation, equals to 0. After rearranging, we can find the expression for the average specific growth rate. Remember the relationship between SRT, average specific growth rate, and specific decay rate? We can substitute the mu average. Then this denominator can also be substituted by equation 1. After rearranging, we can find that SSI minus SSE can be substituted by equation 2, and this gets us equation 3. We can let E be this. Note that the expression in the natural log is essentially SSI divided by SSE. When the recycle rate alpha is far lower than 1, E can be simplified into natural log SS0 divided by SSE. But A typically ranges between 0.25 to 1.5, and this simplification usually does not work. We can plot out equation 3 to find the relationship between SRT and effluent substrate concentration. The blue line is a perfect CSTR, and the red line is PFR. Compared to CSTR, PFR have the same minimum SRT, but can reach a lower effluent concentration at the same HRT after that, and have a lower minimum effluent substrate concentration. From the results of all previous mass balances, we have learned that SRT determines the reactor performance, therefore is a fundamental design variation. It is related to specific growth rate and specific decay rate. Therefore, influences the biomass growth, substrate consumption, wastage, and oxygen supply for aerobic systems. During design, SRT is usually designed by multiplying the minimum SRT that leads to washout by a safety factor. The safety factor can be fairly high and is determined based on design and operation experiences. Compared to conventional systems, a lower safety factor is used for high-rate systems for small footprint, while a higher safety factor is used for low-rate systems for high effluent quality. When you are designing a reactor, you need to make engineering judgment based on feed characteristics, flow fluctuation, regulation, footprint, capital, and operating budgets. But for a system with multiple reactors in series, such as the 5-stage bottom flow reactor designed for biological nutrient removal, the specific growth rate is reactor-specific as the substrate concentration in each reactor varies. SRT, on the other hand, is defined to the entire system. It is the mass of MLSS in all reactors divided by the mass of MLS discharge per time. If we assume that the wastage flow rate is proportional to reactor volume in a Garrett configuration, then SRT is the total reactor volume divided by total wastage rate, same as a single Garrett configuration with no recycling. Can you think about the SRT expression for multiple conventional CSTR with recycling? Yes, it is still the same. And if we assume that the solids concentration is the same in each reactor, the time that solids spend in the reactor is proportional to the reactor volume. In real life, the clarifier is also not ideal. Not all biomass is settled, and there might be some reaction occur as a result. In that case, the SRT needs to include the biomass concentration in the clarifier. It is the mass of biomass in the reactor plus the mass of biomass in the clarifier supernatant, divided by the mass of wasted biomass and effluent biomass per unit time. And this is similar to multiple reactors in series. Because it is hard to unify the SRT for the overall system and the specific growth rate in each reactor, in systems with multiple reactors in series, process loading factor is used. It is the specific growth rate divided by yield. After rearranging, it can be expressed as the mass of substrate consumed per time divided by the mass of active biomass. But because the active biomass is hard to measure experimentally, the process loading rate can be defined as mass of substrate consumed per time divided by the mass of MLSS. Similar to process loading rate, food to microorganism ratio is also used as a design variable. It is the mass of substrate fed to the reactor per time divided by the total MLSS in the reactor. It is still commonly used, especially in anaerobic systems, as it is simple and intuitive. Another design variable is the volumetric loading. It is the mass of substrate fed per time per reactor volume. It is still used to compare similar biological treatment systems treating similar wastewater. Of course, with the help of computational model, we can get much detailed and accurate view of the performance of complex biological systems with different flow rate, wastage rate, recycling rate, or even step feeding and varying aeration.